Welcome back to ofthe Engineering. I'm Oscar, and this is part 2 of Machine Building Basics. Today we're going to talk about motors. The definition of a motor is a device that turns energy into mechanical motion. The energy can be supplied in several different forms, such as fluid, using different types of oils and emulsions, or using air like pneumatic motors. And within many sectors of industry, hydraulic motors are one of the most commonly types. But the one that will be most useful to you as a home hobby machine builder is probably an electric motor of some sort. And today I'm going to show you several different kinds, explain their differences and their uses. Let's start with the most basic and then move up from there. This is probably the most basic motor there is. This is a small permanent magnet brushed DC motor. And they're called brushed because here you can see they have two carbon brushes. And this is to turn the rotor, the part inside the motor that rotates, into an electromagnet. On the outside ring of this motor are two or more permanent magnets. And the magnetic field of the rotor is reverse polarity compared to the permanent magnets, and this is what imparts the motion. But there's more to it than that. Within the rotor there are several coils, and each of these coils is turned into an electromagnet. Now there has to be at least, there can be more as well, and the reason for this is because if there only was two coils, and we magnetize them, then the rotor would move to a stable position then stop. It wouldn't create any rotation. The part that the brush is connected to, I don't know how well you can see that, inside there, is called the commutator. And this actually serves to swap which of the coils are energized. Which means that we energize two coils, it moves a bit. We energize the next coils, it moves another bit. We energize the next coils, it moves a bit more, and so on and so forth. Until we're back to the first set of coils and we've completed a full revolution. Brushed DC motors come in all shapes and sizes. There are motors less than a tenth of the size of this one. And at the cold rolling mill where I work, we have motors up to the size of several hundred kilowatts or several 100,000 watts of power. And within both paper mills and steel mills, it was for a long time really common to use DC motors because it is extremely easy to control the speed of them. The only thing you have to do to control the speed of a DC motor is vary the input voltage. Let me show you. Now this small motor is connected to my lab bench power supply, and the multimeter is measuring the voltage across the windings. So as you can see, at 0.12 volts we have no motion at all. Let's increase it. Now we're at 1 volt. Let's increase it. I'm not really sure how well this shows on film, but you should be able to hear the difference. Now we're at 5.3 volts, 9.9, and now we're at 13 volts. It is also really easy to reverse the rotation of a DC motor. All you have to do is swap the polarity. I don't know if you can see it, but it is rotating in the other direction. Now this can be done in several different ways, either using relays or contactors, or using an electronic device called an age bridge. And I will explain what that is in the next episode of this series when I talk about motor control and drivers. But let's move on to something a bit more complicated than this one. This is a stepper motor. It's one of the most cheap and easy ways to achieve really precise motion in home-built CNC machines, or any other type of machine of your choice. This is also a DC motor, but of a completely different kind of the one I showed you right now on the bench. And the difference is that they don't contain any brushes. Now there is also a type of motor called a brushless DC motor, or BLDC, and they share some characteristics with the stepper motors, but there are also some important differences. Let me show you on the bench. Here I have another stepper motor, but a smaller one. The one I just showed you on my Queen Bee Pro CNC is a NEMA 23 size stepper motor. This is a NEMA 17 size. Now the NEMA sizes doesn't really have anything to do with power, but of course a bigger NEMA motor is generally more powerful. What they do tell you though is the flange size and the location of the mounting holes. So the flange size of a NEMA 17 motor is 42 by 42 millimeter, And the position of the bolts are 31 by 31 millimeter. However, there might still be different size shafts on motors in the same NEMA size. And also different power and torque ratings, usually depending on how long they are. So a thinner motor will have lower power and lower torque than a longer one, since there's less magnets inside. And let me open this up and show you what I talked about when there's a difference between these and BLDC motors. And don't worry, I can get it back together again. And here you can see the first difference between a DC motor and a stepper or BLDC motor. As I showed you on this one, the coils or windings are on the rotor, the part that rotates. On a stepper motor or BLDC motor, the coils are generally on the outside, on the stator. And the permanent magnets in this case are on the rotor. And as you can see, it's magnetic. And it is shaped like a sprocket or cogwheel to guide the magnetism to each of these points. And as you can see, the tops of each of these cogs are slightly offset. They are offset by 1.8 degrees to be precise. And if you have read anything about stepper motors, that might ring a bell. Because stepper motors are generally designated by the amount of steps it takes to complete one full revolution. And the most common amount of steps are 200 or 1.8 degrees per step. And this is what makes the steps. So to achieve rotation in a stepper motor, we can't simply energize two wires and it will self-commutate and automatically move the magnetic field around the stator to turn it. We have to use something called a driver. Something like this. Or like this. But I'll be talking a bit more about drivers in the next episode. But what they do is similar to the commutator of a brushed DC motor. They create a rotating magnetic field. But instead of doing it mechanically, as on the brushed DC motor, they do it using electronics. And they basically energize these coils, one at a time, which moves the rotor 1.8 degrees per time. There's also something called half-stepping or micro-stepping, where you don't energize the coils fully, but only slightly, so you can get the rotor to move just a fraction of a full step. And being able to move the motor one step or a partial step at a time is of course what makes them extremely useful for home-built machines and home-built CNC routers. Because if we connect the output shaft of the motor to either a rack and pinion or a belt or a screw, we can simply tell the motor move this amount of steps and we will know how far the machine has moved and in what direction. This is also a stepper motor, albeit of a different kind, and this is in the NEMA size flange. This motor also has an integrated gearbox, meaning it gives it a lot lower speed but also a lot more torque and more precise control. These are quite common to see in Arduino starter kits and other kits for hobby electronics. Now let's increase the complexity again and talk about servos. This is a common RC servo, and inside here we have a DC motor, we have a gearbox, and we also have the most important thing that actually turns this into a servo, and that is a feedback circuit. So let me just go into control theory really quickly here. Let's simplify it a bit and say there are two types of basic systems. First, we have unregulated systems. And in these systems, we basically say we want 500 RPM. And this can be achieved in several different ways, which I will talk about at a later video. So basically we send the signal for 500 RPM to the motor. Does the motor reach 500 RPM? We have no idea. It might or it might not. Now, generally you have performed some tests before, so you do know that if you tell it to go 500 RPM, you will be at 500 RPM, plus or minus a bit. And then we have servo systems. And the entire principle of a servo system is that it has feedback. And in this case, we have some type of device out here. It might be several different technologies, but we have a device that can sense either speed or angle. And this device sends a signal back to our controller like this. And the signal it sends is the current speed. And if this speed is, let's say, 450, even though we told the controller that we wanted the motor to go at 500 RPM, the controller will keep increasing this signal. And of course, we're not telling the motor to go RPM, we're simply sending a reference, usually voltage or current. And this voltage or current will continue to be increased until this feedback signal reaches 500. And this is a servo system. And now I'm going to show you how we accomplish this in an RC servo. So here we have the gearbox with the output shaft and the input shaft. Here we have the motor, and down there we have our feedback sensor. And in the case of an RC servo, it is a small potentiometer. And as the output shaft rotates, we can measure the changing resistance in the potentiometer, and with the help of that, determine the position of the shaft. And this little circuit is actually the servo driver. It is designed to accept a PWM signal, or pulse width modulated signal. And this pulse width modulated signal tells the servo how many angles to move between 0 and 180 degrees. And these are probably the smallest, cheapest servo systems there is. And they're also relatively precise and can be quite useful. Now, while potentiometers are still used as feedback, both in small hobby systems like this and bigger industrial ones, there are of course other systems that are more precise and more useful. This is a 100-watt servo motor with a built-in drive step. And inside this motor there is something called a pulse encoder. And the pulse encoder gives a specific amount of pulses for every revolution. Generally we're talking binary resolution here, so 1024 or 2048 is quite common, and that means that we have 1024 or 2048 pulses for every complete revolution of the motor. These pulses can be likened to the steps of the stepper motor, but instead of telling the motor to move this amount of steps, we are listening to the pulses, and we're telling the motor to move and then counting the amount of pulses that are fed back to us. And this is all done inside the driver of this servo motor. Servos are used on almost all professional CNC machines. And for a good reason. They are extremely powerful, extremely fast, and extremely accurate. And since you have the entire feedback loop inside the driver that can be either internal or external, as long as you have a solid mechanical system, you have no reason to actually measure the position of the axes, as was done on old school CNC machines. Then you had a DC motor, actually not too dissimilar from this one, and then you measured the position of the axes. And when the position of the axes were where you wanted it, you turned off the motor. Simple as that. And if you find any really old school CNC machines from the 70s or early 80s, this is probably how they worked. There is also something called a hybrid servo. And these started popping up a couple of years ago, mainly from China, and with the definition of a servo system being a system with feedback, then they are also a servo. But what they've done is take a stepper motor and attach an encoder on it for feedback. And this has some upsides, but it's still not really as good as a dedicated AC or DC servo. Because a stepper motor is generally less powerful the faster it goes. and it will lose more steps, basically lose its position more the faster you go with it. Now an AC or DC servo, however, you can simply increase the current and increase the voltage until it's at the correct position. But you can't do that with a stepper motor because then it starts losing steps. What you can do with a hybrid servo, however, and which is implemented in all the better drivers out there, is you count the steps and then you let the motor run for a little bit longer to catch up the lost steps. And this is also what servo drivers does. It keeps the motor running until it's at the correct position that you told it to move to. Now, if you're building a homemade CNC router that I did, steppers can be extremely accurate, cheap and easy to use, and there's absolutely nothing wrong in using them, but you have to know their limitations, such as that they lose steps on high speeds and have the most torque on low speeds. And servos are the opposite. Now I'm going to show you the last motor for the day, and that is a 3-phase asynchronous AC motor. This is a 2 kilowatt 3-phase motor out of a compressor. And this is a whole other animal than the other motors I've showed you. It doesn't contain any brushes, as the stepper motor or brushless DC motor, but it doesn't have any permanent magnets inside of it either. The 3-phase power induces a current in the rotor, the current drives a voltage, and the voltage creates a magnetic field. And to explain this a bit better, I'm going to draw some graphs. So let's start first with just repeating what DC current is. DC current is a fixed voltage. We have 0 or neutral, and we have a fixed voltage. And this might be anything. It might be 5 volt, might be 12, might be 1000 volts, but it's fixed, it doesn't change. AC voltage, on the other hand, changes on a sinusoidal curve. And the only thing sinusoidal means is the shape of the graph, so don't worry about it. And in one-phase AC systems, and we have one live wire or one phase, it changes something like this. And in Europe, the time it takes for this graph to create one full rotation is a 50th of a second. And this is the hertz, or the frequency of the current. So in Europe we have 50 hertz. In North America you have 60 hertz. And this basically means 50 times a second or 60 times a second. Now, however, in 3-phase systems, we have, of course, 3 phases that are offset. And the graph looks a little something like this. Yeah, I completely messed that up. It should be like here. Yeah, that's better. And this is of course only one full wave of 3-phase power. So inside our 3-phase asynchronous motor, we have a series of windings. And they can be connected in 2 different configurations, either star or Y, or delta. And a delta configuration looks like this. So here we have L1, here we have L2, here we have L3. And that means that across each of the windings, we have the voltage that are between 2 phases. And here in Europe, it should be 400 volt AC. Now some countries, like Norway, have 240 volt 3-phase system, but here in Sweden we have 400 volt. On the other hand, in a star configuration or Y configuration, we have 400 volts across 2 of the coils and only 240 volts across each of the coils. And most motors you will find are rated for both 240 and 400 volt systems. But that also means that if you have 400 volt 3-phase, you need to connect it in the star configuration, because if you connected it in the delta configuration, you would actually have 400 volts across a coil only meant for 240, and that would fry it. Now if you have a motor that's classified for 400 and 690, then you'll use the delta configuration for 400 and the star configuration for 690, but these systems aren't that common and only seen within heavy industry. Now in this case, the voltage and current has nothing to do with the speed of the motor. Instead, what determines the speed is the frequency, or the hertz. And like I said, we have 50 hertz in Sweden, meaning 50 rotations per second, or 50 full waves per second. And since the power is constantly changing between positive and negative, this is what creates the rotating magnetic field. Because we will energize each one of these coils in sequence. So when this wave increases, the magnetism increases in this coil, and then the next, and then the next, and then the first one, and then the next one, and so on. And this creates a rotating magnetic field, which of course gives us angular momentum and a motor. 3-phase motors also have something called poles. And poles describe how many magnetic poles are inside the motor. You can have 4, 6, 8, 12, whatever, and the amount of poles determines the speed of the motor. Because the more magnetic poles we have, the less the rotor will move for each full wave of 3-phase power. So where are these motors used? Well, basically everywhere. I have one on my table saw, I have one on my compressor, and I have this one that I will put on my compressor. And within industry they are used everywhere, from water pumps to hydraulic pumps to compressors, of course, to transport lines, to everything. And if you put a gearbox on here, they are extremely useful for high power, low speed operations. Now, to use one of these in your home-built machine, you will need either one of two things, or I should say 3 things. You will need either a contactor, that is basically just a big relay used for turning on and off power loads. You will need a soft starter that I can explain at a later date, or you need a variable frequency drive. And the first two has the downside that you will have a fixed speed on the motor, you can't change it. But if you want to change the speed of this motor, you will need to change the frequency of the incoming power. And the most common way of doing that these days is with a variable frequency drive. And since I've already talked for way too long on this subject, and I've only really barely scratched the surface, I'm going to explain what variable frequency drivers are and other types of drivers in the next episode of this series. So if you're interested, make sure to check that out. And if you like what you're seeing, you know what to do. Till next time.